Warning: lemon essential oil has the capacity to be toxic and can have lasting effects on one's health when concentrated. Be sure to avoid exposure while handling. Essential oils also tend to be highly flammable. Avoid working with a flame and have firefighting protocols at the ready. Essential oils are highly toxic to aquatic life and can persist in aquatic environments. Do not dispose of any waste down the drain. I shall not accept responsibility for any incidents as a result of imitating this video. Hello everyone. Today we will be carrying out a simple steam distillation of lemons. A steam distillation is a distillation variant where the components can be separated below their boiling points at atmospheric pressure. Often, natural products have boiling points above the temperatures at which they begin to decompose, and a steam distillation can circumvent this issue when normally distilling such compounds. Limonene, while not decomposing below its boiling point, can be extracted via steam distillation and is the subject of this video. Limonene is found as a major natural product in citrus fruits and is often used as a fragrance, flavorant, or solvent. Additionally, limonene possesses antimicrobial properties, giving it the potential to aid in preventing food spoilage. Personally, I would like some limonene because it smells great, lemons are cheap, and the distillation is very easy to do. One last thing. I'll be referring to the lemon essential oil colloquially as limonene, even though the essential oil contains several other components in significant amounts. The following chemicals were used for the distillation: tap water, lemons, and sodium chloride. Distilled water is not required for this experiment, as the ions present in the tap water will not distill over with the limonene. It should be noted, however, that any volatile organic contaminants in the tap water will likely distill over with the limonene. Personally, I am willing to accept this risk of contamination. The lemon peels were zested over a grater and the total mass of zest was recorded before the distillation. A simple distillation setup was then constructed. A stopper was used in place of a thermometer, as knowledge of the current vapor temperature is not a requirement for a steam distillation. The round bottom flask was heated using direct contact to a hot plate, which is not very efficient and should have rather been done with the oil or a sand bath. It should be noted that the stopper was momentarily replaced with the thermometer and its adapter to ensure that the temperature within the flask was rising. The condenser was cooled with frozen cool drink bottles, which was likely overkill. The lemon zest was gradually loaded into a 500 ml round bottom flask. The zest was quantitatively transferred using boiling water, and the flask was slowly filled up such that the lemon zest could be completely suspended in the water. The use of boiling water reduces the time it will take for the flask's content to start boiling after heat is applied. Additionally, the boiling water was added slowly to reduce the risk of the glass cracking due to thermal stress. Normally, such a precaution is not necessary, given that laboratory glassware is made of borosilicate glass, which drastically reduces the degree to which thermal expansion can occur, but better safe than sorry. Quantitative transfer of the lemon zest is also not necessary, and was largely done as a force of habit. Once the zest was suspended, the still head was attached and heating was initiated. Foil was wrapped around the round bottom flask and the still head to retain heat and to prevent premature condensation in the still head. The original plan was to allow the distillation to continue until no more oil distilled over. However, the oil coming over in the final stages of the distillation had a heavy, unpleasant smell to it. As a result, I halted the distillation at this point. This is either the result of most of the limonene being removed, leaving only foul-smelling terpenes, or the presence of decomposition products due to overheating. I believe it to be a combination of both. The distillation had been running for almost an hour and I was using a very high heat setting on the hot plate. In the end, over 200 milliliters of distillate was collected with a thin oil layer on top. The distillate had a pungent citrus smell and was smelled by wafting vapor towards my nose, as concentrated essential oils can be damaging to one's health. To separate the organic and aqueous layers, a separatory funnel was used. The distillate was loaded into a separatory funnel and some brine solution was added to increase the ionic strength of the aqueous layer, improving the separation of the oil from the aqueous layer. The lower aqueous layer was discarded and the upper organic layer was directly drained into a storage bottle. Ideally, the organic layer should have been dried, but for my purposes of just obtaining some limonene, this would not have been necessary. If I were to perform a drying step, washing with brine solution would have likely been the best option. Use of a solid desiccant with subsequent filtration would have likely resulted in massive evaporative losses. The storage bottles used are old contrast bottles for imaging and have rubber septums as stoppers. Though the rubber is of excellent quality, previous testing with turpentine showed that organics will penetrate the septum within a week, allowing for turpentine to be smelled. Additionally, the exposure to organics caused the septum to swell considerably, but this was partially reversed by the septum being exposed to air over a few weeks. A solution to the organic penetration problem is the use of Teflon tape between the bottle and the septum. Teflon is highly impervious to almost all compounds, and a repeat of the turpentine test with Teflon tape has prevented the penetration of turpentine, and I have yet to smell turpentine over a month later. The use of Teflon tape proved effective in containing the smell of limonene, and thus the limonene itself. Given a starting mass of 126.0 grams of lemon zest, and the mass of oil having been extracted being 1.7 grams, the yield of this extraction is 1.3%. This low yield was expected, as the extraction was prematurely stopped and the oil itself is only found in very small quantities in the lemon rind. Okay, we know why steam distillation would be used to obtain limonene, but why does it work? Why does boiling lemon zest in water allow for the collection of essential oils? All liquids have a capacity to volatilize to some degree. The degree of this volatilization can be related to a liquid's vapor pressure, where the vapor released by a liquid is able to exert pressure. The greater the vapor pressure, the greater the volatility of a particular liquid. This is why one can smell limonene in zested lemons. The oils within volatilize and make their way to one's nose. Vapor pressure is proportional to temperature, and this relationship is one of the major factors to why steam distillation works. Using the Clausius-Comparion equation, the expression for how vapor pressure of a liquid varies with temperature can be derived. For an increase in temperature, the temperature-dependent part of the equation will be negative, resulting in a positive expression which corresponds to an increase in vapor pressure. A graph of vapor pressure versus temperature can be constructed. Using the NIST chemistry webbook, the enthalpy of vaporization for limonene can be plotted as a function of temperature to obtain a regression line and its equation. This allows for the enthalpy of vaporization to be predicted for any temperature. There is some uncertainty in the points used in the graph, along with uncertainty in the graph itself, but this should not influence the general trend I would like to show. Using the Clausius-Comparion equation, the relative final vapor pressure was plotted against temperature. The graph shows that there is an exponential increase in the final relative vapor pressure as temperature increases, which matches what is expected for other volatile compounds. A temperature difference of 25 degrees Celsius to 100 degrees Celsius would result in a 187 times increase to the relative final vapor pressure of limonene. This is one of the reasons why steam distillations work. The vapor pressure of the volatile components are drastically increased, making volatilization more favorable. Furthermore, for immiscible components, their vapor pressures act independently of each other. Raoult's law indicates that the vapor pressure exerted by a volatile component in a solution is proportional to its mole fraction in said solution. For a binary mixture of water and limonene, assuming that they are miscible with each other, the following equation can be used to describe the vapor pressure of the binary solution. However, limonene and water are, for the most part, immiscible. As a result, the limonene and water will contribute independently to the vapor pressure, irrespective of their relative quantities. This allows for small amounts of limonene in the zest suspension to still exert a large vapor pressure, irrespective of the amount of water, increasing the degree to which it is found in the vapor phase. The last factor at play is the formation of steam itself. The continuous formation of steam pushes the gas above the round bottom flask, containing the limonene vapor, towards the condenser, where it and the steam can be removed from the gas phase via condensation. This continuous removal of vaporized oil prevents the net rate of volatilization of the oil from reaching zero. Another possible factor is azeotrope formation with the water, but I believe this to be negligible given the tiny mole fraction of dissolved limonene. While steam distillations are rather incredible in their function, there are two major disadvantages. First, compounds must have a sufficient vapor pressure to distill over with steam. If the compound is not volatile enough, it will not make it to the condenser, and thus will not be collected. For a compound to be volatile enough to distill over with steam, its vapor pressure must at least be between 5 to 10 torr at 100 degrees Celsius. Limonene possesses a vapor pressure of only 10 torr at 54 degrees Celsius. Second, steam distillations are stupid slow. While the distillation performed in this video only took around an hour to complete, this is because there's a rather tiny amount of limonene present within the lemons. For a far larger amount of substance needing to be purified, the time needed for purification can quickly become unreasonable. This is further slowed if the vapor pressure of the compound is low. NerdRage once used the steam distillation to purify products from a Grignard reaction, which was reported to take over a week to purify. I would also like to talk a bit about the essential oil itself, with a particular focus on limonene and its uses. The three major components of lemon essential oil are the monoterpene hydrocarbons, d-Limonene, at 60.7%, beta-pinene at 12.6%, and gamma-terpinene at 10.3%. A large variety of other compounds are also present, such as alcohols, aldehydes, various monoterpenes, and sesquiterpenes. Limonene shows promise as a less toxic and renewable alternative to petroleum solvents. Particularly, it was demonstrated that limonene can be used as a substitute for n-Hexane in the extraction of lipids from olives, with slightly improved yields over n-Hexane. The use of hexanes as a solvent has become increasingly undesirable due to its toxicity. Additionally, limonene and essential oils in general have displayed antimicrobial properties in the form of growth inhibition, allowing for the preservation of food, especially against microorganisms which have gained resistances to widespread antibiotics. Thank you for watching. Hopefully this is going to be the first of many experiments displayed on this channel. I am open to any feedback or recommendations, as this is my first formal style video, and while I've done several practical reports, this is my first one in video form. Once again, thank you, and I hope you have a good day. Also, I'm no longer going to be using a fence gate as a stand.